Podgórski. I am a PhD candidate at the Institute of Geophysics at the Polish Academy of Sciences, and today I am going to tell you how are satellite images made. So we will start with an introduction to the satellite images. What are they? A satellite image is a photograph taken with a camera that is located on a satellite. Today we will only be talking about the images of Earth, but it is good to know that a large part of what we know about other planets of our solar system, about Mars or about Jovian moons, is known from images that were taken by satellites who were orbiting these planets and moons. And why did even people start taking satellite photos? Nowadays, it's mainly scientists and cartographers that are interested in these data, but in the past it was the intelligence, the spies, who pioneered the satellite imaging technologies because they needed it to know what's going on in the enemy countries. It's also worth noting now that the satellite images are often very pretty, aesthetic. You can see here it's an image of Iceland, which looks nice, I think. It was taken with, it's a screenshot from Google Earth, which I will use a little bit more today. And Google Earth is a nice program. You can download it for free and use it at home to look at satellite and aerial images of the Earth. And what is a satellite? The one device that carries our camera that takes photos of Earth. So according to a general definition, a satellite is every object that is orbiting a planet, that is, it travels around it. So by definition, our moon is a satellite, and more specifically, natural satellite of the Earth. But very much more often, and also throughout today's lesson, a satellite is an artificial satellite, that is a man-made object that is orbiting around the planet, traveling around it. We are using satellites for very many tasks. They are used for example, for GPS. It relies heavily on satellites, and so does satellite TV. So if you have this white dish that's picking up satellite TV from the air, it is taking signals from a satellite. And of course, today we will focus on the satellites that are taking images. And here you can see below the moon an artist vision of imaging satellite, Landsat. It's one of the most popular, most extensively used Earth imaging satellites. And let's start with a satellite image, a more zoomed in one than the one of Iceland previously. And I have taken a screenshot again from Google Earth of the Polish polar station in Hornsund in Spitsbergen. And what we can see on this image, aside of course of the Polish polar station itself, we can see a number of information regarding the photograph we are looking at. So in the middle there is this disclaimer, image copyright 2016 digital globe. It is a statement of attribution. It attributes this image you are looking at currently to a specific company, and as each company operates its own satellites, it can allow us to trace which satellite has taken the picture. Below, in the lower bar of this image, you can see some metadata. We will talk about metadata later on, but now notice, I left it in Polish, but it's no problem, that is a date of image acquisition. In this case, it's 17th August 2013, and then coordinates, geographical coordinates of the area we are looking at, as well as the height over the sea level. In this case, it's 1 meter because we're very close to the coast, and the height of viewing spot. So how far above the ground are we when looking at the world at this level of zoom. And what we can see as well is that the image is a little bit grainy, even though we can tell apart very specific features such as buildings, fuel tanks, the white things on the beach. We can see how wide is the beach in this area. We can see where are the mosses growing in the vicinity of the station. And now I have taken another picture of the very same area, Hornsund Fjord and Polish Polar Station, but this time I have zoomed out. So you can see in the lower right corner that the height of viewing spot has changed to 15 kilometers. And so did the coordinates, because now the middle of our picture is a bit somewhere else. And so did change the acquisition date to the 31st of December 2016, as well as the source. Now we have a statement saying image Landsat Copernicus, which means that this image comes from a Landsat satellite. And regarding the image itself, you can see now that the beach that have been quite wide became a very thin strip, thin light, bright strip around the land, that we cannot see the buildings anymore. And the graininess is really quite similar, even though the features we are looking at are much bigger. So those two images have a different spatial resolution, and which means that keeping the same graininess of our image, we can have bigger features on one picture and smaller features on other picture. So now moving to a little bit of theory, what is the spatial resolution of an image? First, I have to remind you or tell you what a pixel is. So a pixel on a digital photograph is the smallest part of a digital image. It is true for satellite imagery that comes from space, but it is true as well for the images you are taking with your mobile phones or cameras, and it is true for images you can see on a monitor of a computer, on a computer screen. And on a satellite image, the size of the pixel, that is how big an area fits into a single pixel, is spatial resolution. And here you can see two examples. The first column of this diagram shows us the reality as seen through a camera, through a digital camera. So there are some buildings, a lake, some rock, and we are looking at it through a grid of pixels in which, in the first case, on the top row, each pixel has a side 10 meters long. It means that we can, for example, fit half a building into a single pixel. It means that we can fit 1, 2, 3, a lot of pixels into the lake. And what is important here is that every single pixel can only have one color inside. So if you can see pixels which contain both the lake and some of the white, say, snowy area, in the pixel, although we can, with our eyes, see the difference and the border, the pixel will only have one color in this place where there is a border between two areas. And it means that this color will be the mix of the two. So that is why on the photograph, in the photograph column in the top row, you can see that those pixels that land wholly into the lake have the same color as the lake, the blue like the water. But the pixels that have both the lake and the surroundings are having a light blue color. That is the mixture of the blue of the lake and white of the surrounding snow. The same case is with the buildings. Two pixels, when there is a pixel that is covered in its entirety by a building, it has the red color of its roof. But when we have a pixel that has both building and snow, it's becoming light red. And the same principle applies on the lower picture that has a bit worse spatial resolution, because a single pixel this time has a side of 20 meters. That is twice as long, and it means that in a single picture of the lower, in the single pixel of the lower image, you can fit 4 pixels of the upper image. And that obviously influences our result. As you can see on the photograph, the one below, you can see much less detail than on the image above. So then nowadays the lake almost disappears because there is not a single pixel with which is entirely within the lake. And the places where the lake shares a pixel with a bit of orange rock actually becomes green, because more or less that's what you're getting when you mix those two colors. It is also way harder to tell where exactly buildings lie on this image, because in the picture above you can easily see the red rectangles and they say, yeah, this is a building here, it's quite accurate. But here below it's much harder to tell. The color is more dissolved and the pixels are much bigger, so it's hard to say exactly where the building is. And now, what does this spatial resolution depend on? Because there must be a reason why some satellites have smaller pixels and other satellites have bigger pixels. So it depends primarily on two things. The first are camera's parameters. So the better camera, the better resolution. But today we won't be talking this much about cameras because you can put any camera at any satellite. It doesn't really matter. What is more interesting is the distance between Earth and the satellite that takes pictures, which influences the resolution regardless of the camera's quality. And on this picture, you can see a satellite, the black box. It carries a camera that has 3 pixels. It's all quite theoretical. The field of view of the camera is a triangle when it looks from above onto the Earth. And when the distance is small, let's say 600 kilometers, the base of this triangle is short. And this length of land has to be divided into 3 parts, and it means that every single of this part will have, say, 30 meters length. And you can fit 30 meters of area into a single pixel. But when the distance is large, let's say 36,000 kilometers, the base of the triangle becomes very big. But we still need to squeeze it into only 3 pixels. So every single of those pixels will be much bigger. And we'll have, for example, 1,000 meters. That's quite a difference, and that's what we have seen on the previous slide. On the closer one was the better resolution. The farther one is the worse resolution. So now another question you might want to ask: why does anyone even build satellites with bad resolution if you can build satellites with good resolution? Now you can see the 2 values at the bottom of the picture. They are not really random. I could have put some nice values such as 100 and 1000, but I've decided on 600 and 36,000. And why did I do so? Because these are the most popular orbit heights, distances for taking Earth images from satellites. You can see on this picture I have found on the internet, it depicts all the satellites that are present above the Earth. And you can see there are 2 concentrations of these satellites. The first is the swarm that surrounds the Earth close to the surface. It is known as the polar orbit, and it has around between 100 and 1,000 kilometers away from the Earth. And the other one, the nice ring that surrounds the planet, is a geostationary orbit, another very popular orbit for taking images, and not only images, which is 36,000 kilometers from Earth. And now I will show you those 2 orbits and how do they work. Let's start with the polar orbit. It is an orbit, it's a lower one, between 100 and 1,000, as I said. And wait Now I have to figure out the animation. Oops. Yes, you should see now the animation, and now you can see the Landsat satellite, the very same we have seen in the beginning, traveling the Earth. You can see that it's scanning a narrow area of the Earth, so the part that gets colored is essentially what the satellite sees and takes photograph of. You can see its tail. It doesn't have this tail, it's only for purpose of animation. And you can see it got a little bit faster because it's traveling really fast around the Earth. So, and it's really close to the surface, so it cannot cover a big area at one pass. So you can see that it's traveling very quick. Let's do it again. It's traveling quite fast. And every time it takes it some 100 minutes to make a full circle around the Earth. And the satellite is kept at a constant orbit. As you will see in a while, the satellite travels the same circle, but the Earth below it is rotating. So it can cover more and more different terrains despite not moving itself, because the Earth is rotating below it. The good thing, the pro of the satellite, is a good spatial resolution, which is achieved because we are flying quite low. And but the bad thing about this is that we can revisit the very same place only once in 10-15 days. Another thing worth knowing is that the International Space Station, the one with astronauts on board, is also orbiting a polar orbit. And the other kind of orbit is the geostationary. It was the nice ring I have shown you on one of the previous slides. And this time a satellite is rotating at the same angular velocity as Earth. You will get another animation now with the geostationary orbit. You can see those three white balls orbiting around the Earth. These are the geostationary satellites. You can see that they are orbiting at the same speed as the Earth, which means that, first, from our point of view, if we were to look up at the satellite, they would be immobile, so to say, relative to Earth. They are hanging over the very same spot of the planet all of the time. The good thing about this is that since they are not changing the place they are looking at, they can take an image of the very same place even every 15 minutes. So you can monitor the Earth almost live, almost in real time. The bad thing about them is because they are very far away, 36,000 kilometers. The spatial resolution is quite bad. But it's not really a big problem, because this orbit is used for meteorological satellites, which don't need good spatial resolution, but the meteorologists like to watch clouds and weather unfold in the time scale of exactly minutes and hours. The other thing this orbit is used for is TV. For example, when a satellite is supposed to beam European TV, it is placed in a geostationary orbit that faces Europe. Then it can broadcast European TV to Europe, but it cannot broadcast anything to America because it doesn't see America, because it cannot move relative to the Earth. So now that we have learned the two distances, let's say 600 and 36,000 kilometers, let's talk a little bit, let's introduce a bit of physics and learn why are they so. In case of the polar orbits, we have quite a big choice of orbits. Between 100 to 1000, 600, 800 are the most popular. In case of the geostationary orbit, there is no choice. That's why they look like an elegant ring around the planet. They have to be on the very same distance from the Earth, all of them, if they want to keep their angular speed exactly the same as the Earth. And what is angular speed or angular velocity? It is a measure of speed of a rotating object measured in angles. That is, how large part of a circle does a rotating item cover in a travel in a given time, say in seconds. Let's compare it to the traditional velocity, the linear one. In the image, in the part of image above, linear velocity v, a satellite is going 100 meters in 1 second. It means its velocity is 100 meters per second. It's simple. But with the angular velocity, we can have, for example, two satellites traveling around the Earth in circles. Both of them are going to cover 1/4 of a circle. But one of them is going on a higher orbit, so it has to travel along the long arc, which is long. And the other one is below, and it's traveling along the short arc, which is shorter. So the two satellites are having different linear velocities because they cover different distance in the same time, but they still cover 1/4 of their orbits. So the physicists needed a measure of this to compare the two satellites, and they noticed that when an object travels 1/4 of a circle, it can be said that it travels 90 degrees, because 1/4 of a circle is corresponds to an angle of 19 degrees regardless of the circle's size. That's why the angular velocity is expressed in angles per second. And that's how we can compare satellites that are or planets that are rotating at that have very different sizes and sizes of their orbits, but still we can compare which one of them is rotating faster and which one of them is rotating slower. So now with this knowledge, we need to find an orbit. We need to know one more thing, that every orbit above the Earth has its specific speed, angular velocity, that has to be maintained by a satellite if it wants to keep its height. If it changes the velocity, it changes its orbit, and thus if the satellite speeds up, it changes an orbit to a different one. And every orbit has its own angular velocity. You can see like here, the satellite wants to travel on a geostationary orbit. That is the one that has the same angular velocity as the Earth. So that's the black angle on the image. The arrow at Earth shows us angular velocity of the Earth, so how big an angle does Earth rotate at given time, and we want our satellite to travel the same angle. So we need to choose an orbit that allows the same angle in the same time. I didn't mention that. So we need to choose the orbit, to calculate the orbit that has the same angular velocity as the Earth. And that's why it turned out, that's why it's 36,000 kilometers. Not exactly 36,000, but more or less. And that's what physicists calculated. If we want to have a satellite that travels at the very same angular speed as the Earth, it has to be at this height. If it was going to be put lower, it would be too fast. It would rotate around the Earth a few times before it makes a single rotation. That's what happens with polar satellites. And if we would put it too high, it would be too slow, and the Earth would, so to say, run away from the satellite, and it couldn't hang over a single spot for the whole of time. Okay, we know where a satellite is. We know why is it there. So let's back to our satellite images. What happens to a picture once it's taken? Because if we have a satellite with a camera on the orbit, it's located some hundreds of kilometers away, and we need to get this image somehow back to Earth. At the very beginning of space exploration, it was every satellite was carrying a camera, which of course was not digital because there were no digital cameras back then. So a capsule with a film was simply dropped from the orbit to the Earth and caught by helicopters or landed in the ocean and was then retrieved. Nowadays, of course, everything is beamed down in a radio transmission, every image, to a ground station. There is a host of stations around the planet which have a big antennas aimed at the satellites, and they receive their transmissions with images. And this image that gets to the Earth is actually composed of a number of bands. Each of bands is an image taken in a single wavelength. For example, red, green, blue, like in your images. If you ever tried to edit a digital image on your computers, you'd notice that it has channels, bands, red, green, and blue. And the same case is with the digital images from satellites. But they also have more bands, because red, green, and blue are the ones we are using to make an image that's in the so-called real colors. That's what we would see as humans. But there are also spectra of electromagnetic radiation that humans cannot see, such as ultraviolet or infrared. And there are satellites that do take pictures, images in these bands. But now that we have the whole bunch of these bands, we can merge them, and this can be done both in a specific programs designed for satellite imagery processing, but also in any generic graphic program. We are just taking those three bands and telling a program to make them into a real color, true color image. And that's what we're getting here. Red, green, and blue mixed together give us this neat image of Horizont Fjord. And that's exactly the same thing that happens in your digital camera once you take a picture. It's actually three pictures merged together. So we've got the color picture here on the ground. And you can look at this image and say, wow, yes, it's a Polish polar station, I can see it. But the computers cannot. Computers do not know what can they see on the image, and we have to tell them where on Earth, like where on the surface on the planet, a picture is located. And at the very beginning, I was telling you about the metadata, the data about data. That is another pack of information that is beamed down from a satellite together with the images, which contains information such as time of acquisition, some of those things that I have shown you on the bottom of a picture. Time of acquisition, the exact location, very precise, of satellite when the picture was taken, the height of satellite with very good precision. And they are used to automatically georeference or georegister an image. So if we know that this image has the middle of this image is 77 degrees north, 15 and something degrees east, we can place it onto this neat little globe you can see when you open the Google Earth, and it is pasted there and it's georegistered. So if you go to a place that you know is Polish Polar Station Horizont, you will see an image of Polish Polar Station Horizont. But sometimes researchers, particularly geography researchers or cartographers, need a very precise georegistration, because that thing which is done with automated algorithms, with metadata, is good, is certainly good enough for Google Earth, and there are no errors, but sometimes researchers need way better precision and accuracy. So in that case, if you have a picture like this with the Polish Polar Station and you want to have it very precisely pinned down on the planet, you need to go to the field. You need to get your hands dirty. You have first, on an image, you identify points that are easily found in the field. For example, a corner of a house. In this case, I have chosen two corners of houses in the station. Then you go out with a GPS device and go to the very same place live in the real world with this to the very same corner of building with your GPS receiver and note the coordinates. Once you have many such points, I just pointed two for clarity, but usually you would need like 6, 7, or 8 to georeference a picture with good result. you go back to your office, get your picture up on a computer, and tell the computer in a specific program designed for georeferencing that this single pixel, which contains the corner of the house, is located at 77 degrees 0 minutes 492 seconds north and 15 degrees 32 minutes 5540 seconds east. You do this with all the points you have collected and hit run, and then it is georeferenced with very good accuracy, much better than the automatic thing. And that's also how it has been done with early images, because there were not much computers, or they weren't this clever to do this themselves, and people were just going out to the field, picking up coordinates and putting them into the computer. Aside of putting the image in the right place of the planet, georegistration, regardless of whether it's automatic or handmade, embeds distance information into the picture. So if you have a raw picture without georegistration, even if you know that a building on this image is 20 meters long, you cannot measure it in the computer. Once you georegister it, and it exactly knows where every pixel is located, it can easily calculate the distance between two pixels, and so you can use the measuring tool in Google Earth and measure the distance from your home to school, just because the images are georegistered. And that's all for today. Thank you for attention. I hope you liked the lesson, and see you again in a different class.